Okay, today we're going to talk about some equations related to electromagnetic radiation. Electromagnetic radiation is everything from microwaves to infrared, like heat vision, like you see on video games, visible light, ultraviolet light, and then up into X-rays. Those are kind of the ones that they expect you to know. But all electromagnetic radiation. And, this c here that we're going to talk about is known as the speed of light, but it's really just the speed of any electromagnetic radiation. So we have here some variables that, essentially, if you have a combination of these variables, you can move the equations around to find any other part of it, okay? So this one relates the wavelength and the frequency. So when things move in a wave, you've seen this before, it's kind of like peaks and troughs. And that's how, the top parts are the peaks, the bottom parts are the troughs. And then a wavelength is you mark off a peak and then the same spot on the next peak. Like that. And then like from spot to spot, that's a wavelength. It's one whole wave. And so, you have wavelength and then frequency because it's how big the waves are and then how many come by. Usually when I'm teaching this, I talk about one day I was out on a run and a guy was standing on an overpass on I-20 and just sort of leaning over and looking out at the cars. And, I stopped and I asked him, buddy, are you okay? Are you doing all right? I thought he was maybe wanting to jump. And he looked at me like I'm a little crazy, as you would. But he says, oh no, I'm fine. My job here is to count the frequency of trucks coming down I-20. And so what he was doing is every time a truck would come under the underpass, he'd count it. And he'd been, out there, and he was going to be out there kind of all day counting. And so that's the frequency is, if you mark out a spot on something, just any fixed point, it's how many complete waves or trucks or really anything come by that point in a certain time. That's the frequency, okay? And so that's why frequency, when you look at the unit, it's per seconds. It's how many comes by per second. So you get your wavelength, which is in meters, your frequency in per seconds. You multiply them together, you get meters per second, which is c, the speed of light, speed of electromagnetic radiation at 3 times 10 to the 8th meters per second. Now, so the answer is always 3 times 10 to the 8th meter per second in a vacuum. And most of these equations we're going to be assuming are going to be in a vacuum. And so the longer wavelength you have, the longer the waves, the lower the frequency because, they're longer. And so not as many of them can get by a spot in a certain amount of time. And so longer wavelength, lower frequency. And if you have a lower frequency, when you come down into this energy equation, if the frequency is lower because the wavelength is longer wavelength, lower frequency, lower energy. So when you bring it down, when you bring a low frequency down into this one, the energy is not going to be as much. So what that means is sort of the lower energy bands have longer wavelengths. So like your radio waves and microwaves, those are all going to have really long wavelengths, and they're not going to have as much energy, and they're not going to be, they're not going to have that energy. They're not going to be dangerous. Whereas you get up into X-rays and gamma rays at the far end, it's bad stuff. Those are carcinogenic, and those can cause cellular change. Okay, so if you want to look at that for a second. The E is just the energy in joules. H is Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And so, since you have your frequency per seconds, joule seconds times per seconds gives you joules, and that's your energy in joules. So I have 475, and that is just awful. That looks like chicken salad, so there you go. So I got 475 nanometers. So what I'm saying here is I've got some electromagnetic radiation at 475 nanometers. Now, the first thing I need to do is switch it into meters. And so 475 nanometers times 1 nanometer is 1 times 10 to the negative 9th meters. Always remember, nanometers is negative nanometers. And so that is 4.75 times 10 to the negative 7th meters. So that's the first step right there, is since usually when you get it in nanometers, you need to switch it into meters. And then I can find the frequency. So since C equals lambda nu, lambda being the wavelength, nu being the frequency, and I know the answer here, I can divide both sides by the wavelength to get the frequency. So I'm going to do that. So C, and there you are. So I'll just plug into that. 3 times 10 to the 8th meters per second divided by, I'm going to put this in parentheses, 4.75 times 10 to the negative 7th meters equals the frequency, like that. There you go. And then 3 times 10, 8 divided by parenthesis 4.75 times 10 caret negative 7. So I get 6.32. It's a 3 times 10 to the 14th hertz. Right like that. And so your frequency should be a larger number. Your wavelengths are usually your smaller number. Can't think of another situation where that wouldn't be true. And then if I want to know how much energy I have, I just move it down. And so I've got Planck's constant, and I'll try to 6.626 times 10 to the negative 34th joule seconds times 6.32 times 10 to the 14th hertz. And then I'm just going to multiply times. So that's going to be 4.18 times 10 to the negative 19th joules. So that goes from, they give you a wavelength in nanometers, use it to find the frequency, take your frequency down to find the energy. Not too bad.